known researcher, knowledge representation and reasoning, who's traveled quite a few universities, including Drexel University, and prior to that he worked at Cardiff Research Lab. He's been funded by NIST, DoD, NASA. He also has been named the Data Fellow by the National Consortium of Data Science and co-chaired Wharton's International Conference on Logic, Programming and Non-Monotonic Reasoning last year. And today he'll be talking about the new direction in his research with cyber-physical systems.
Thank you very much, Julia. I should definitely shorten that by just keep adding things what they come up and I don't shorten. Okay, thank you very much, everyone, for having me here. I'll try to speak up. Sometimes I tend to drone off, so if you can't hear me anymore, let me know. So yes, I will be really talking about a project that has been going on for a few years now, over different incarnations. It's really at the intersection of cybersecurity and artificial intelligence and knowledge representation. It's something that I find quite interesting, quite challenging. It started early on as a project related to power generation and distribution systems on board military ships. So it was funded in a few different ways from the US Navy. Later I started looking at automotive systems, and then we looked more broadly at the trustworthiness of cyber-physical systems in general. So, like I said, various inclinations. Luckily, I was quite lucky to have bits and pieces of funding from different sources, which made it more sustainable. So let's start from, whenever I talk about cybersecurity and knowledge representation and cyber-physical systems, I always have a guarantee that there will be people who will not be familiar with some of those terms, so I will be spending some of my time trying to make sure that we're all on the same page. So first of all, the concept of cyber-physical system. So when we talk about cyber-physical system, we are thinking of some generally sophisticated, complex system consisting of a combination of computing components and components that I typically call physical. So these are components that act directly on the environment or interact directly with the environment. So in a cyber-physical system, you have these logical components. Logical components through actuation may drive physical components, may drive physical phenomena, and then through sensing, they may get back from the physical environment information, which in some way is then translated back into some more digital or logical form, typically for the decision-making side. Just so we're all on the same page, a simple example is the heating system in a house. You can do it as a thermostat, and a heating system or the HVAC system. So the thermostat has a physical part, the temperature sensor, but it also has a pretty substantial nowadays computing part. In fact, some people use those thermostats for cyber attacks. So, definitely they have some non-trivial computing power. But then when the thermostat decides that, for example, it's getting too cold, it's going to send a signal to the heating system, and now the heating system is really, for the most part, a purely physical component, which is going to start burning, say, natural gas in order to generate heat, and then it's going to have fans that are going to circulate the hot air. So a typical example of cyber-physical system. Did I go back? Didn't go back. Okay, sorry guys. The challenges with cyber-physical systems are multiple and non-trivial. So cyber-physical systems, because of this combination of logical components and physical components and the interactions, they are often difficult to describe, difficult to understand. In particular, sometimes you just have components of the individual components of the cyber-physical system whose behavior you understand only in part. You don't exactly know how they're going to behave under some conditions. It may sound crazy, but we'll talk about it later, hopefully. It happens. But even when you understand how each component behaves individually, now if you have a multitude of them interacting with each other, understanding the overall behavior of this system also becomes quite non-trivial. So people working in cyber-physical systems, practitioners, engineers, and other operators, and so on, they often have the problem of, okay, how do we design this system? How do we maintain this system? How do we know what issues may occur? How do we even operate the system? So, as an example, one of my earlier projects or earlier pieces of project in this direction was the one I mentioned with the US Navy. So they have these military ships, as you can imagine, very scary weapon systems that I cannot know about because I don't have clearance yet. They have them. And for the longest time, this is stuff the Navy folks told me, for the longest time, the people who made decisions, they really only cared about the weapon systems. You have to make sure that they're secure, you have to make sure that we know how to operate them, you need to make sure that we understand how the various components interact with each other. And then slowly, they started understanding that these weapon systems actually depended completely on, or highly, on the power systems. For example, the power system of a ship will power the air conditioning system. First time they told me, in my head I was like, okay, who cares? The sailors are going to just be hot if somebody attacks the power generation system and they cannot run the AC system. It so happens that the air conditioning system is fundamental for cooling down the weapons. So if you manage to attack or affect somehow, or if there's a malfunction, no attack, on the power generation distribution system that's going to block the air conditioning system, now you cannot attack. Even worse, you cannot defend yourself. It's really, it's kind of crazy. And so over time, over the course of about 5 years, these Navy decision makers went from who cares about the power systems to they're super important and we have to classify any project that's related to them. That's quite interesting. So what we did in this case was one of the first steps towards understanding how the power systems worked. So first, the realization was because the power systems are not something people really worried about up to that point, they're all built from off-the-shelf components. They have actual PCs like ours running, in fact, Windows XP, because then they have their upgrade requirements. A computer with Windows XP is really not a good choice. And they have PLC, programmable logic controllers, which are the same PLCs that you may find in a power grid, on the power grid, or in a large company. So really off-the-shelf components. So the first step was understanding which components are involved in the power generation distribution of a military ship, how they're connected. See, these are some diagrams. This is stuff I found online. I cannot show anything else. So these are, these systems are connected in various ways. Some of them are connected using Ethernet. Some of them are connected using Modbus, serial connections, and so on. And we had to build a model of these connections. So really, first we had to build a framework that allowed us to model power generation distribution systems in general, and then we modeled some specific cases. And then we used available public databases of vulnerabilities, threats, mitigations, to understand which components of one of these CPS might be affected by a known vulnerability, what we could do to mitigate that, And most of all, something that I don't think I'm showing here, these big diagrams that describe the CPS, they actually go a bit above your traditional model of a CPS. They also describe how, I should say, which components are involved in performing certain missions of the ship. Missions such as reconnaissance, or attack, or running away. I don't know the actual terms or the precise terms. So that eventually we could build a system which they use for vulnerability assessment. So they want to be able to ask the question, okay, suppose now I understand that, let's put it this way, suppose this vulnerability came out, okay, in how bad of a shape am I? Can I still attack? Can I still defend? Can I still, run some other mission that is important to me? And so all of this was done by modeling the system and connecting all this with available knowledge about vulnerabilities and so on. Now, that was a specific solution that we came up with. But then over time, both I and other people began to understand that what we had done there was important in more general terms. In general, many cyber-physical systems are critical systems. They're frequently built from off-the-shelf components. So what issues we had on the ships, we may have somewhere else. On top of that, as I was explaining earlier, as you were composing a cyber-physical system, for a new ship, for example, or a new piece of a power grid, you want to design it in such a way that you're going to know which components should be in, and why, and what the final behavior is going to be. So that means that you're going to have, and many experts are involved in doing something like that. People slowly understood that we needed a common shared vocabulary for all these experts to use in order to talk to each other and to talk about their community, what worried them, and what goals they had. So NIST, the National Institute of Standards and Technology, a few years ago, 2 or 3 years ago, 2 or 3 years, I think, began an effort. They gathered many experts related to CPS, and they began very long discussions on this shared vocabulary, which eventually became this shared framework, the NIST CPS framework. In this framework, so this framework provides everybody who's interested in CPS with a way for talking about a CPS in, like I said, this shared way, common way. So here I'm just really giving you the basics. There's a couple of volumes available online from NIST, and they're free, so you can read them at any time. They go into a lot more details that I will be covering. So this is just the surface. So at the very top of the framework, we have a collection of aspects. These are aspects of the cyber-physical system that experts are interested in. And some experts will be interested in some aspect, other experts may be interested in other aspects. The trustworthiness aspect, of course, we frequently talk about trustworthiness, right? Especially in cybersecurity, is one aspect. Functional aspect, basically, is my CPS going to behave? Is it going to function properly? Is it going to do what I expect? Timing aspect, is it going to produce what it needs to produce at the right time as opposed to being slow or fast? Maybe the function is correct, but it's too slow or too fast. For each aspect, they identified one or more concerns, which are sub-elements of these aspects. For example, in the context of trustworthiness, to achieve trustworthiness, you have to ensure safety, you have to ensure security, and so on and so forth. By the way, they have more aspects and more concerns, but this is what I normally can fit on a slide, and that's what I normally use. And then for security, well, to ensure security, you have to have both physical security and cybersecurity. And then in cybersecurity, you have the typical split in confidentiality, integrity, and availability. To ensure that one concern is satisfied, if that concern is split into other sub-concerns, you have to ensure that those sub-concerns are satisfied. And by calling them out, giving them names and giving them definitions, which you can find in their volumes, you can make sure that when people talk about trustworthiness, well, now everybody knows what they're talking about. When people talk about cybersecurity, sometimes different people have associated slightly different meaning to cybersecurity. Here it's clear that they're talking specifically about the CIA triad. All of this up here is, so aspects and concerns, is really, so it's a hierarchy of concepts, and it is independent of the specific CPS that you're modeling. That's the goal. Once you have a sufficient number of aspects and concerns, everybody will be able to talk about any CPS using these terms and their hierarchical relationships. To describe a specific CPS, they use properties in the framework. So properties are statements about the CPS and its components that might be true or might be false. And these properties influence whether the corresponding concerns are satisfied or not. For example, in a particular CPS, I might say that the SAM, I'm going to tell you later what it means, the SAM is a component. Uses the encrypted memory, and the camera must use the encrypted memory for the confidentiality concern to be satisfied. If they don't, then the confidentiality concern is not satisfied. If it's not satisfied, then immediately the cybersecurity concern is not satisfied, and all the way to trustworthiness not being satisfied as a whole because it's missing one piece. So these properties essentially describe what the requirements, that's another word they sometimes use in this CPS framework, the requirements, they describe the requirements on the CPS. So even though the CPS framework is a really nice piece of work and it really helps understand the CPS and talk to each other about the CPS and its requirements, it has some shortcomings. First of all, it's a piece of text that people are supposed to read, understand, and then essentially run in their heads while they're talking to other people. So open questions are, well, how do I how do I formalize it so that instead of arguing with somebody else over our shared interpretation of these terms, what if I can just ask a system, oh, and by the way, also, instead of having to worry about this relatively complex hierarchy of concepts and figuring out what the ramifications are for a specific CPS, what if I could just ask a question and have a system answer that question? So, going back to the example of the Navy ships, can I still defend myself, or am I in trouble now? So one of the shortcomings was computability, executability of this model that they created. Also lack of mathematical formalization. There's still ambiguity in the descriptions they associate with some of the terms. But also, even though the properties, the last layer at the bottom of the previous slide, allow you to describe requirements on the CPS, they still lack that knowledge about the surrounding environments that often is needed. Sometimes you have properties that depend on each other. So maybe, I cannot have the heating on and the air conditioning on in the same heating and air conditioning unit. Hopefully you can. I guess you can't. That's not something that's clearly visible in something like this. You don't have those dependencies. So at some point, NIST became interested in looking for ways to address these open problems. And so we have worked on it for the past year. We came up with a solution that's based on knowledge representation, a branch of artificial intelligence, which essentially aims at creating mathematically precise representations of knowledge that can be consumed directly by computers. To answer questions about a cyber-physical system, to essentially run these models, we use logical inference. So we reduce everything, the computation of consequences, computation of links between properties and the consequences of those links to performing logical inference. So at the very high level, when I say knowledge representation, there's, well, it doesn't say too much. So specifically, the approach we used is relatively new in the context of knowledge representation in that it uses two quite different, quite separate, two parts of knowledge representation that evolved quite separately over time. Let's put it this way. It combines ontologies and constraint satisfaction languages. So both are, even though they evolved quite separately for a very long time, both shared similar roots. They're both rooted in one way or another into relational databases, mathematical logic, and to some extent in operations research. For the past few years, people have realized that they can be used together to build rather sophisticated models of the world around us, or fragments of the world around us. So what I'm going to do next is I'm going to give you a very quick intro on these two aspects of knowledge representation. So ontologies, first of all. The way my view of ontologies, which is not necessarily identical to that of other people, is that to me ontology is a word that denotes formal models of some domain of interest. Some people become more specific, but I like to look at it at a very high level like that. A little more specifically, these are formal models that consist of four types of elements: classes, objects or instances, relations, and actions. So classes, I believe we all know what they are. These are sets of objects of interest. For example, I could have a class of computers that denotes all of the computers that I can possibly ever build. And a subclass of it is the class of laptops. Okay. Then for objects, individuals, or instances, I use these as three synonyms in this context. These are the elements of a class. This laptop here is one instance of the laptop subclass. And so by applying inheritance, you can conclude that it's a computer. Once you have instances of a class, now you can describe properties of those instances, properties of those objects. By using attributes, for example, I could say, my laptop weighs, I guess, 6 pounds. I don't know, it's a guess, but it weighs 6 pounds. And also by establishing relationships between objects. For example, my laptop is next to that other computer screen. Next to is a relationship in this case, or that laptop belongs to me. The laptop and me are both objects, and the relationship of ownership establishes a link between us. These are pretty classical components of an ontology. And then oftentimes people will also use axioms. Axioms are statements, formal statements, that establish a link between the truth value of certain, I'll just say certain relationships. It's a little bit of abuse of notation, but the truth value of certain relationships and the truth value of other relationships. For example, if I say, it's probably too small for you guys to see, but I could say, if a PC has a certain operating system, and that operating system is affected by a certain vulnerability, then by all means, that PC should be considered as being affected by that vulnerability. So I'm taking something that I know about the operating system and the operating system running on a computer and the vulnerability affecting the operating system, and I infer new knowledge about which vulnerability is directly affecting my computer. So these axioms, when they become sophisticated, are a natural fit for constraint satisfaction. So the expressing, representing these axioms, when they are complex, is a natural fit for constraint satisfaction languages. So again, very quick primer on another concept. So constraint satisfaction languages are languages in which we formal, mathematically based languages, in which we write statements about a world of interest, or a fragment of the world of interest. We have quantitative constraint satisfaction languages. You can think of equations, just for simplicity. So here, we're going to have statements that are based on numerical variables, quantitative variables. And then there's a branch of qualitative constraint languages, or constraint satisfaction languages, where the variables are Boolean, so they may have true, their values are either true or false. And you may have statements such as this one that we can read as if Q then P, or Q implies P. Meaning that if Q, then by all means, if Q is true, then by all means we should believe that, or conclude that P is true. And in recent years, there has been substantial work on hybrid languages that combine quantitative elements and qualitative elements, so that now we can talk about Boolean variables and numerical variables in a single language. Without going into details, the way in which these languages are interpreted, so the semantics of these languages, is very roughly speaking based on three concepts. Concept of theory. So a theory T can be viewed as a set of statements written in that language. So if it's a quantitative statement, quantitative language, it's going to be a set of equations. Or it could be a set of implications if it's a qualitative language. And then the notion of model. So a model is defined as some assignment of values to the variables of our theory that makes all of the statements in the theory true. And that applies, again, if once you pick a language, then you have to fill in some of the gaps and specify a few more things. But that's a very high-level view of what a model will be in general in constraint satisfaction language. And then the key is the notion of entailment. So once you have a theory, and you T in some statement S, you can say that the theory entails that statement, and you write it like this, if that statement is true in every model of the theory. Or really, in some constraint satisfaction languages, you may have a type of entailment that says that S is entailed if it's true in some model of the theory. So if I have a theory that says if Q then P, and then it tells me, look, Q must be true, then a trivial model of this theory is a model that says that Q is true and P is true. Q is true because, well, we're saying that it's true. That's what the theory says. And P is true because of the implication. Then a conclusion that I could draw by using entailment is that the statement P or Q must be true. Because we already know that P is true, and we even already know that Q is true. So trivially, the disjunction P or Q is true. So by using entailment, this is a very powerful technique, powerful device. We can essentially derive new knowledge from an existing theory. New is a bit much of a word, but we can derive information that wasn't clearly and immediately visible from the theory. So now to demonstrate how we used all of this, so going back to cyber-physical systems, how did we use all of this to solve those open problems in the CPS NIST framework, NIST CPS framework, and in general to reason about cyber-physical systems. So let's focus on a use case that we sometimes use for our work on the CPS framework. So this is a lane keeping assist system from a car. Stuff that you can actually find in cars nowadays I'm told pretty frequently. My car is not fancy enough. But you're going to have some computing component that has a camera attached to it, and it monitors it monitors what's ahead of the, I guess what's ahead of the car, but I'm not sure, to make sure that the car stays in the lane that it's on. And if it detects that it's steering a little bit out of the lane, then it has direct control of the steering wheel, so it can either make the steering wheel vibrate, or in the fancier cases, it can actually turn the car and keep it in the lane. So there are two components. I'm showing you the simplified versions of the lane keeping assist system. There are two components in the simplified version. A camera, and what we call the SAM, Situational Awareness Module, which is a fancy term for the computing component of it, decision-making component. So the camera, in this example, in this use case, comes in two variants, a basic camera and an advanced camera. Either cameras are capable of recording video at 25 frames per second and at 50 frames per second. Again, this is just a notional example. But the basic camera, because it's cheaper, will tend to drop frames if it tries to record at 50 frames per second while it's using encrypted memory. So camera and SAM can also use encrypted memory, and they can also have security in this use case. So as for the SAM is the component that's directly responsible for setting the recording rate of the camera, because it is the decision-making part. And then it processes the video from the camera, and it sends some output to the steering wheel, again, let's say, to just keep the car within the lane. Okay, so how do we model something like this? So the first step is, how do we use the NIST CPS framework to model it? So the diagram that I showed you earlier, I didn't say it at that point, and we didn't go into details, but it's actually a diagram of the lane keeping assist system. So the parts at the top we already went through before. Now you can see more the meaning of these properties. So the SAM uses encrypted memory, the camera uses encrypted memory. These are properties that must both be satisfied so that the system maintains confidentiality, because you never know. We know of cases in which cars have been attacked by hackers, so confidentiality definitely makes sense in this context. And then to address the functionality concern, the system must work in such a way that the camera stores all frames. Imagine if the camera is not capable of reading in all the frames, it may miss the key moment where it should steer the car back in, and it may allow it to go into the other lane. At that point, it's too late to react. So that would affect the functionality of the system, meaning okay, the system is really not behaving the way it should. So first step is creating an ontology that models all of this. So this ontology is, so for these two layers of the diagram, the corresponding ontology is a general purpose ontology. In ontology lingo, I guess we could view it as an upper ontology. So we have a number of classes. The important ones are the concern class, which describes all of the concerns, and the aspects subclass. So we're saying that aspects are really concerns, which captures the way the NIST experts really view aspects and concerns. So eventually we figured out that was the right way to model it. So aspects are a special case of concerns. In particular, they're the top level concerns. These are classes for when you want to capture a specific concern, you're going to create an instance. For example, let's talk about the availability concern. The availability concern is going to be one instance of class concern. The fact that the availability concern is a sub-concern of cybersecurity. It's described by means of a relation, which here we call includes concern. That relationship will say, the sub-concern of, what do we have here? Oh, this was aspect functional. So a sub-concern of aspect functional is the functionality concern. So we'll describe it this way. Again, this is all the upper ontology, so the CPS, the part of the model that's independent of a specific CPS. How do we link the bottom part, the actual model, the actual description of a specific CPS? This is done through class property. Class property is the class of all properties that you may want or need to define. And there is a relation called address by, or address by property list, which is attached to the concerned individuals. So for example, the integrity, I don't have it here, but this is about the integrity concern. So this diagram, or this figure here shows that the integrity concern is addressed by these two properties, which happen to be the two properties that are related to having secure root, using secure root of SAM and CAM. So combination of classes, classes, objects, and relationships captures this whole diagram. That's basically exactly what's in the NIST framework, all of these components. The key that's missing here is how to establish the relationships between properties so that we can show how they influence each other. And that's what I'm going to show in the next couple of slides. So first, this is a detailed view of the functionality concern. So remember the functionality concern up here. This was satisfied, or was addressed by the property of recording at constant frame rate or not dropping frames. Unfortunately, I had a couple of different versions of this figure, so sometimes I have the old terminology. So in terms of that ontology that I showed you on the previous slide, the functional aspect includes concerned functionality, which is addressed by property whose name we don't need to try and read, but that's exactly the property about not dropping frames or storing their frames. On top of that, and now we're going to start moving towards axioms. Remember, what we want to be able to do is we want to be able to link the truth of this property to all the way up to the functional aspect. So we would like to be able to say things like, well, if this property is not satisfied, there's no way that the functional aspect is satisfied, right? And vice versa, if this property is satisfied in this particular diagram, then the functional aspect will be satisfied, which means I'm okay with the way the system works, I don't need to worry. All of this is accomplished by means of essentially this, you can see that this is a forest. In fact, in the more complex situations, when you add sufficient details, it's going to become a graph. So propagation of satisfaction throughout this graph is accomplished by means of axioms. And here I'm showing you a couple of samples of these axioms. But in the next slide, we're actually going to go into details into the more interesting axioms. These are the axioms that can be used to describe how properties are connected to each other, how they influence each other, and also something we're quite interested in when we talk about CPS frameworks in the context of CPS, in the context of the CPS framework. How can external events affect our CPS? For example, what if a cyber attack comes in and we know what the cyber attack looks like? Okay, what now? Going back to the Navy ships, which missions can I perform now that I know the system has been attacked? So we have created for a convenient specification of axioms about properties and about events that may occur. We have created what we call an axiom specification language. which consists of these classes of statements. I'm not going to go through all of them, but I'm going to give you some samples of the important ones. So we can start from the bottom here. So that's there's a important link in the LKAS system, link keeping system, that tells us, look, if the camera is using encrypted memory and it's recording at 50 frames per second, and it so happens that the camera that's doing all this is the basic model, then the camera is not going to be able to store all frames. It's going to start dropping frames. So using our specification language, we'll write it in more or less this form. This is an impacts negatively, so the keyword is here, impacts negatively. And this says, well, if you're using encrypted memory, you're recording at 50 frames, so not 25. This is just either or, so there's no other choice. If this is the basic camera that you're using, then this impacts negatively, so these are our properties. This impacts negatively the property that the camera stores all frames. Okay? Specifically in the case of this property, there's some implicit assumption if you think about it. We're really only concerned about stating in which cases the camera will not store all frames, because the underlying assumption is if none of those conditions apply, then the camera will be storing all frames. Right? We are interested, just because of the specific use case, we are interested in describing when things may go wrong, and we want to assume that in all other cases things will be okay. So the second set of specification statements, the default property value statements, allows us to say, and I'm not showing the sample here, but allows us to say, look, this property here, the property of storing all frames, that will default to true. So by default, we're assuming that we can do that. But keep in mind there may be statements, such as this one, that may tell you that in some cases there are exceptions. And then, I'm not going to go into the details of these, but the last few sets of specification statements, axiom specification statements, allow us to describe actions that may occur and their effects, meaning which properties they will make true, which properties they will make false, and in fact, even some conditions under which events may be triggered. For example, in Unix, if you kill process 1, you're going to trigger a reboot, I guess, or a shutdown. It's been a while since I played with that. But that's something that you would, you might describe in this way. Now, if process 1 is dead, then a reboot is triggered. This axiom specification language is something that we call, that we use for convenience specification. Under the hood, this is translated to a constraint satisfaction language, and here I'm giving some samples of that translation. So this essentially completes that diagram that I started earlier with ontologies, so classes, objects, and relations. Then the axioms, and I would say, well, we can use constraint satisfaction languages for them. In fact, we use axiom specification, an axiom specification language for it, a bit more abstract, but then we translate it to constraint language. Okay. And by the way, any questions? Sometimes I get ahead of myself. So, so essentially, at this point, we have built a model specifically of the LKES system. But we have the elements that allow us to build models of arbitrary cyber-physical systems in such a way that we can outline the various dependencies between concerns, the influence of properties, and on top of that, now with the axiom specification language, we can describe how properties affect each other and how actions affect properties. Next step is, well, we would like to be able to do reasoning over that. Meaning we would like to be able to answer questions about this system. I forgot to enable the encrypted memory. Is my system still going to work, or am I in trouble? That kind of questions. So to answer these questions, to do reasoning, we use logical inference or entailment, depending on how you want to see it. At the core of all this is the fact that now we have, so if you think of our model, we have an ontology consisting of classes, individuals, relations, and then we have these axioms. Now the ontology is written, encoded using a certain language, some ontology specification language. The axioms are described using a constraint satisfaction language. It so happens, if you look at things from a sufficiently high perspective, or if you have the right tools under the hood, that all of these are logic-based languages. They share, even though they came out of very different traditions, they share many commonalities. It is possible to. They share a lot of commonalities that allow us to actually combine them in a certain way and do reasoning across their boundaries, reasoning across the whole model. So in the reasoning use case, what we will be using is a notional configuration in which SAM and camera use encrypted memory and secure boot. We're using the basic camera, not the advanced one. The SAM is telling the camera, okay, you gotta record at 25 frames per second. Questions that the experts are typically interested in are, well, the key ones are, well, is my functionality concern satisfied? Really meaning, is the system working properly? Is the, well, at the concern level, and on top of that, if you think of hierarchy, is the functional aspect satisfied? This is really where we're asking, is the system working properly from all aspects? Then what are the ramifications of certain events? For example, a cyber attack. And if certain events have undesirable ramifications, how can we mitigate them? Okay, so these are the types of questions we focused on. In particular, so as I was saying, all questions, all reasoning is reduced to performing logical entailment over a theory. Remember I talked about theory? So once you have a theory, you can carry out logical entailment or do logical entailment, apply logical entailment to decide which other statements are true and which other statements are false. The theory now, well, the theory is a collection of statements, logical statements, and it so happens that our ontology and the axioms can be translated in a relatively uniform collection of statements in the same language. So in a theory. So in the case of the concern tree questions, for example, is the trustworthiness concern satisfied? Is the functional aspect satisfied? That boils down to taking a theory consisting of the ontology, the axioms, plus some bits and pieces describing the specific query I'm asking, and checking if certain statements are true, if certain statements follow from that. For example, this is a simplified version of the language. You'll see the actual language later. But for example, I may be saying, so is it true that the trustworthiness concern is satisfied? Assuming that this is a statement in my language. We have so I didn't mention it before, but we also have something that I find interesting, this partial design synthesis question, where we say, here's a model of my system, here's how I'm planning to configure it, but I'm not sure about, say, these couple of properties. I'm not sure if they should be true or false, I'm not sure if we care. But what I know is that my system needs to be trustworthy. So what truth value should those properties have? Should they be true, should they be false? So this is what we call the partial design synthesis, because we are partially completing the design of the system. And this can also be done using entailment. And then what if scenarios and mitigation scenarios, that's what I already described. If this event happens, what now? Is my system still going to be trustworthy? I can do that with entailment. How do I mitigate the fact that now my system is no longer trustworthy? What can I do? Which actions can I perform to work around that? I might need to reflash a firmware, for example. So now let's look at the practical side of things. So in the LKS system, concern tree question could be, well, given the same configuration that I described before, we could be asking, so is the functionality concern satisfied? So if you look at this fragment of the diagram, so this is actually kind of a tricky question. So the functionality concern is satisfied if the camera stores all frames. Here I'm not saying anything about the camera storing all frames or not in the configuration. However, I'm talking about the camera recording at 25 frames per second, and I'm talking about using the basic camera, and I'm talking about encrypted memory. So if you think of that axiom specification language and the statement I wrote earlier on the negative impacts on recording of or storing of all frames, you may remember that we said if you're recording at 50 frames per second on a basic camera with encrypted memory, then you're not going to be able to store all frames. But by default, you should assume that you can. So unless you have some stated exception, then you will be recording all frames, storing all frames. So once you take that into account, then definitely one should assume that the camera is storing all frames, which in turn means that the functionality concern should be assumed to be satisfied. And so this is the actual syntax that we use. So then we actually have an implemented system, so I took some screenshots. So this is going to conclude that indeed the functionality concern is satisfied under these conditions. What about the functional aspect? So looking at the diagram, if I know that the functionality concern is satisfied, I should be able to propagate that up and conclude that the functional aspect is satisfied. Some of the axioms that we have in the system, which are actually general purpose axioms, they propagate satisfaction and dissatisfaction up the concern forest. These allow us to do just this. So from the fact that the functionality concern has been proven to be satisfied in the previous slide, now we can conclude, and you see the output here, that the functional aspect is satisfied. And let me call to your attention one element that I glossed over earlier. There's a 0 here. So remember I said we also want to be able to determine the effects of actions. What happens if, for example, a cyber attack occurs? So this model, I really haven't talked about it because it would take another 2 talks just for that. This model can also reason about the state of the CPS over time. Okay, so you don't just have truth and falsity in a static sense of those properties. Truth and falsity can change over time, and the ramifications can change over time. The model of change over time is discrete. So this 0 indicates that in the initial state, discrete state of the evolution of the system, then the functional aspect is satisfied. And there was a similar 0 for the functionality concern, we just didn't call it out. So when does this time step become important? Well, it becomes important when I have actions that do things to my system. So let's say that in the previous, let's say enrich the previous case. Let's say that now we know that a cyber attack just occurred. And that cyber attack is known. We're assuming that we have that knowledge. If we don't, then it's another very interesting problem. Then that attack hacks the SAM and forces it to request a recording at 50 frames per second. Okay? This can be done by means of axioms, so I'm not going to spend time on it. You know, depending on how familiar you are with logic, you may already be able to interpret this. But this can be all encoded using the axioms that I showed earlier, the axiom language that I showed earlier. Now, supposing that we know that the attack occurred and we know what the attack does, then the next question, just like my Navy counterparts always want to be able to ask is, okay, what now? What can I do? What can I not do? In particular, in the use case, is the functionality concern satisfied now? Is the functional aspect satisfied now? So if you think about it, we have an action that tells us if you're recording at 50 frames per second on a basic camera with encrypted memory, then you are gonna lose that ability to store all frames. Right? So in terms of the diagram, this tells us I'm no longer storing all frames, and it's down here. When you're no longer storing all frames, the functionality concern is no longer satisfied. Okay? Your system is not really doing what it should. And in turn, if this is not satisfied, then the functional functional aspect is also not satisfied. Once again, satisfaction or lack of satisfaction that moves up the tree, up the forest. And so this is what this is just the output showing us that that's what the system includes. This is a list of concerns, aspects, and properties that are not satisfied. So the final question I was asking, almost done. The final question we were asking earlier is the mitigation question. I'll actually have two variants of that. So the simplest one says, okay, how can I mitigate the effects of this cyber attack? So let's say that we enrich the model of our system with two more actions. We can swap the basic camera for the advanced one and vice versa. Sort of makes sense. It sort of was an underlying assumption since the beginning when I said we can have the basic or the advanced camera. It is possible to write very few axioms, one or two axioms depending on the language, to describe this action and say, oh, you know what, this is what that action is going to do. And by the way, we can also write actions that tell us, by the way, you can also decide which action you want to perform, and you can perform really any action in any combination at any time. This is what we call the mitigation generation module. For those of you used to planning, this is really very close to a planning module. If we add, remember, we're still talking about intelligence. So if we take the ontology, the actions, and the query, and if the query includes the mitigation module that says essentially, well, okay, you're allowed to come up with any combination of actions that you think are useful, then entailment in this situation will allow us to derive this answer that I hope you can see here. This is actually the internal name of the action. This action says disable the basic camera, meaning you have to start using the advanced camera. I cut it in the screenshot, but this actually, this is a mitigation for the scenario in that the moment you switch camera, the moment you start using the advanced camera, then the frames are once again all being stored because the advanced camera is not affected by that ramification of using encrypted memory and recording at a high rate. Therefore, the functionality concern is satisfied, and therefore the functional aspect is satisfied. To make it a little more interesting, and I know experts often are interested in this kind of behavior, this model and the corresponding constraint languages that really drive the reasoning are also capable of returning multiple solutions, multiple options when they exist. So for example, let's enrich the scenario by saying that there is also a patching action. We can patch the SAM, and when we patch the SAM, this is not really a case in which we completely remove the attack or the vulnerability. But we may force, by patching it, we may force the SAM to record video at 25 per second fixed, to request a recording at 25 frames per second. It's not going to be able to decide anymore. We're forcing it, imagine tweaking a flag inside the SAM. But that's another action that's available. At that point, we can again ask our model, so how can I mitigate the effects of the cyber attack? And if you look at it from a theoretical perspective with entailment, and if you look at it from a practical perspective with the implemented system, you will obtain two solutions. One is that of, well, just patch the SAM. You patch the SAM, but keep the same camera in, keep the basic camera in. If you patch the SAM, you're going to go back to recording at 25 frames per second, and everything's fine. You're not going to be missing and dropping any frames. Or replace the basic camera with the advanced camera. Notice, in principle, there's a third solution. You could both patch the SAM and replace the camera. That, in principle, that would also work. I don't think I had it in the 2 slides before when I showed the mitigation module, but if you pick the right constraint satisfaction language, and there's a whole set of them available which work very well for this, there's a way to say, and by the way, find the set of mitigation actions that's the smallest. Okay? So this solution is produced by having that additional action in. So there is in principle a third candidate solution, but it's not a solution. So it's not something Intelligent would return, and definitely not something the system returns because it's redundant. It's kind of an uninteresting solution. But of course it can be true. So, and here I'm concluding. So in conclusion, what I hope I demonstrated is that, first of all, cyber-physical systems, very complex piece to deal with. Many people are concerned about them for various reasons. The NIST, the agency, has worked on a framework that allows us to talk about CPS and talk about our worries when it comes to CPS and talk to other experts in a uniform way. But it has some shortcomings. And so by using a combination of techniques from knowledge representation and applying them to the context or domain of cybersecurity, we have been able to achieve a couple of interesting things. We've been able to create mathematically precise models of our CPS, which, by the way, could also include probabilistic behavior and uncertainty. They already include uncertainty. I'm just not describing that. These models are also, sometimes they're called directly executable models. These are models that we can immediately query for answers, and these answers may involve some non-trivial reason. There are many applications of this, of course. So right now we're using it to use cases, for small use cases. We're applying it to military ships, automotive systems, and power systems. There's not all done by me, but people at NIST are going in many different directions. There are also very interesting opportunities, and I'm talking to a few people about this now, in terms of cybersecurity and cyber risk. Because if you have a cyber physical system and you would like to understand the cyber insurance aspects of it, first you need to understand the risk of it. But to understand the risk of it, you need to understand what may go wrong. So which properties influence the behavior of your system. So it's quite interesting, but it's something that we've just started discussing. And this is just a quick screenshot of our really bare bones implemented system. It's more of a prototype for us to play with. But essentially, if you plug in the right ontology axioms and query up here, then you can run a query and it will automatically produce the results that I was showing. Okay, that's all I had. So thank you very much, first of all. And let me know if you have questions.